Have you ever wondered how the sun's warmth reaches us here on Earth? It's not like there's a giant pot of boiling water up there. The answer lies in a fascinating process called radiation heat transfer. Radiation is how heat travels through the emptiness of space. Unlike conduction, where heat travels through direct contact, or convection, where heat travels through the movement of fluids, radiation can travel through a vacuum. Think about it. The sun's energy travels millions of miles through space to reach us. This same principle applies to many things we experience daily. From the warmth of a bonfire to the heat radiating from a light bulb, radiation is all around us. Now, how do we measure this radiant heat? Scientists have developed a formula to help us understand and calculate this amazing phenomenon, the Stefan Boltzmann law. Don't let the fancy name scare you. It's simpler than it sounds. The Stefan Boltzmann law states that the total energy radiated per unit surface area of a body across all wavelengths per unit time is directly proportional to the fourth power of the body's absolute temperature. This might sound complicated, but it can be represented by a simple formula. This formula might look intimidating at first, but don't worry, we'll break it down together. In the next section, we'll explore what each of these letters represents and how they contribute to understanding radiation heat transfer. Get ready to unlock the secrets of this fundamental law of physics. Let's break down the Stefan Boltzmann formula piece by piece. First up, we have P, which represents the power of radiation. This is the amount of energy radiated per second, measured in watts. Think of it as the strength of the radiation. Next, we have E, which stands for emissivity. Emissivity is a measure of how efficiently an object emits radiation. It's a value between 0 and 1, where 1 represents a perfect emitter, also known as a black body. For example, a shiny mirror has low emissivity, reflecting most of the radiation that hits it. On the other hand, a dark, matte object has high emissivity, absorbing and emitting radiation effectively. This is why you'll feel warmer wearing a black shirt on a sunny day compared to a white one. Section 4. Real-life radiation, from the sun to your toaster. Now, let's look at S, which represents the Stefan Boltzmann constant. This constant has a value of approximately 5.67 times 10 to the minus 8 watts per square meter per Kelvin to the fourth power. It's a fundamental constant of nature that links temperature to the amount of power radiated. Finally, we have A, which stands for the surface area of the object, and T, which represents the absolute temperature in Kelvin. The larger the surface area and the higher the temperature, the more radiation an object will emit. Think about a toaster. The heating element inside has a high temperature and a large surface area, allowing it to efficiently radiate heat onto your bread. Similarly, the sun, with its massive size and extremely high temperature, radiates an incredible amount of energy, providing light and warmth to our planet. Section 5. Infrared Wonders. Seeing the unseen heat. You might be wondering, if we can't see radiation, how do we know it's there? Well, we can't see all types of radiation. Visible light, the colors we see, is a form of radiation. But there are other forms, like infrared radiation, which we can't see with our naked eyes. Infrared radiation is what we feel as heat. Special cameras, like thermal imaging cameras, can detect infrared radiation and create images based on temperature differences. These cameras have many applications, from detecting heat loss in buildings to helping firefighters locate people in smoke-filled environments. By understanding infrared radiation, we can develop technologies that improve our lives, demonstrating the importance of grasping the concepts of radiation heat transfer. Section 6. The importance of understanding radiation. Understanding radiation heat transfer is crucial for various aspects of our lives. From designing efficient solar panels to developing advanced medical imaging techniques, this fundamental principle of physics plays a vital role. Engineers use their knowledge of radiation to design spacecraft that can withstand the extreme temperatures of space. Architects consider radiation when designing buildings to optimize energy efficiency and maintain comfortable indoor temperatures. By grasping the basics of radiation heat transfer, we gain a deeper appreciation for the world around us and the technologies that shape our lives. So, next time you feel the warmth of the sun or the heat from a radiator, remember the fascinating science of radiation at play.